Yeah, good afternoon, all. So, in the last class, we discussed about the few of the applications of the C13 spectra. Okay, so uh, I think means it is a very important question in the exam point of view. Okay, so a few of the examples we have seen in the last class, like where the C13 spectra is applicable, right? So it is having the means so many applications like to study the reaction mechanism and to study the conformation analysis, okay, and to identify the isomers, like what is it? Isomers in the sense where the chain isomers or the positional isomers, right? The functional group isomers, all these structural isomers, right? So you can differentiate the structural isomers and geometrical isomers and the stereoisomers. Also, you can differentiate with help of the C13 spectrum. Okay, so for example, here you see differentiating the geometrical isomers. So what are the geometrical isomers generally? Where the cis trans isomers. In the olefins, you can see this geometrical isomers in the olefins, right? So the cis trans, like here, the cis, uh, okay, the cis carbon and the trans carbon. They will show the different C13 chemical shift values here. So based on that, you can be able to say which isomer is that. Okay. So like for example, here in this particular compound, right? So here is one, two, yeah, two pentene, I think, right? So two pentene, and here also two pentene, but the geometry, this the stereochemistry is different here. In the first compound, where this compound is, right? So trans configuration, right? So here is because here these two hydrogens are in the opposite direction. So it is trans 2 pentene here. And here is two hydrogens are in the same phase or the same side. So it is said to be the cis 2 pentene, sorry, pentene, right? Cis 2 pentene and trans 2 pentene. So if you see the chemical shift values of the various carbons in this particular two isomers here, geometrical isomers. Yes, is it audible here?
Yes,
Okay,
sir.
so yeah, so, okay, fine. So here you see where the C1 carbon, if you see the trans, okay, so the values are given below with the C1 carbon methyl here, right? Okay, this particular, this methyl and this methyl here, right? So you see the same molecular formula. In both cases, you can see the same molecular formula, but where the spatial arrangement of the groups or the atoms are different. Based on that, you will observe the different what is that the different chemical shift values here, right? So here the C1 carbon methyl chemical shift values. So if you see in the trans configuration, right? Here is it is 17.9 here, delta 17.9. And in the cis configuration, where it is the same methyl group here, where the 12.59, the chemical shift values observed is 12.59. Here is a 17.9. So there is a 5 value difference. So this is due to the orientation or the attachment of that particular methyl group here. Okay. So here in this particular trans configuration, right? You know that all these are the configurational isomers. Okay, so we have the two, means the isomers are the two types here. Okay, the dynamic isomer with the conformational isomers and configurational. This classification is based on the energy. Okay, the stereochemistry. In the stereochemistry, you are coming across in the first means in the first semester with the stereochemistry. Okay, so the isomerism. So the isomerism, it is classified in based on the various factors here, various criterias. Okay, so based on the energy, you can classify the stereoisomers, right, into two types. That is, one is a what is it? Conformational isomers, conformational stereoisomers, and configurational stereoisomers. Okay, conformational stereoisomers and configurational stereoisomers. So in these stereoisomers, right? So these are the in these stereoisomers, the difference is the arrangement of the atom, right? The spatial differentiation of the arrangement of the atoms. Spatially differs. Spatially means the distance between the atoms. Okay, here in this, uh, for example, in the trans, you can see the distance between these two hydrogens here, right? So this much difference, this much distance is it. For example, you just to take it as 1 centimeter, 2 centimeter, other one, for example, right? 1 centimeter, for example, right? Okay, and if you see here, these are closer, right? These are far away. So if you say the distance is 1 centimeter, but here these two hydrogens are means closer here, right? So then you can see the means the distance between these hydrogens. It is less than this trans configuration, right? So you say it is 500, right? Sorry, 0.5 centimeter. Or if you take this as a 2 centimeter here, this is 1 centimeter. Okay, so this is the this means we call this is the spatial arrangement. Okay, spatial, S-P-A-T-I-A-L, spatial arrangement of the atoms. So, okay, so this these are called as stereoisomers. So, right, so where the differs in the spatial arrangement is called as stereoisomers, and these stereoisomers were classified into two types based on the energy here. Okay, so one is the okay, so the stereoisomers. Okay, stereoisomers, yes, sir, for example, and the criteria is the energy. Okay, here is the criteria is the energy here. So based on the energy criteria, you can classify, right? Here is a configurational isomers, right? So configurational, and another one is a conformational isomers, configurational and conformational. So what is the difference between these? Right? Here is a conformational. This is a configurational. So what is the difference here? Here the configurational isomers, right? Configurational isomers, they won't interconvert from one conformer to another conformer. Okay, for example, you take RS configuration, EZ configuration, okay, DL configuration, right? So here, for example, here is a some compound, okay, having the means the chiral compound you are taken A, B, C, D, for example, here, okay. So it is going to right. So this is okay. Yeah, what is that? R, for example, and where the another is a D, for example, right? Okay, the enantiomers. Okay, these are the enantiomers here, right? So these won't interconvert from one conformer to another conformer, right? At to 60 or below 100 degrees, sorry, 100 kilocalorie energy, right? So these are called the configurational isomers and conformational isomers. Like you take cyclohexane here, okay, other what is that alkanes, right? So here. Here is some group X you take here. They will easily interconvert from one conformer to another conformer at room temperature. Okay. So where it is the X is in the equatorial orientation. Here the X is in the axial orientation. Right. And to interconvert this conformer to this conformer, it needs only 60 kilocalorie, right? 60 kilocalorie energy, and it will be takes place at room temperature, 27 degrees Celsius. Or the room temperature, we say it is a room temperature here, right? But these won't interconvert, means confer configuration isomers. They won't interconvert from one conformer, means conformer to another conformer at room temperature or at low energy. That's why these are called configuration isomers. These are called conformation isomers. Okay, so here these geometrical isomers are the configurational isomers. Means they won't interconvert. The interconversion from here cis to trans is not takes place at the normal conditions like the normal room temperature or the uh, below 100 kilocalorie energy, right? But in the cyclohexane, the very rapid interconversion, already we discussed in the last class, right? To study the conformational isomers with help of the C13 spectra. Means at a very high temperature, okay, high temperature, a rapid interconversion is takes place. So you will get only one signal for particular compound, means for axial and equatorial, right? At a very low temperature, minus 100 degrees Celsius, right, or the minus 40 degrees Celsius, you will get the two signals here, right? So means at low temperature means the interconversion, conformer interconversion is very slow. That's why. So the instrument can easily recognize or identify the differentiation of that the different conformers, and it will be give the signals according to that the configuration here. Okay, so like that here. So for the differentiation of the geometrical isomers, we have you can use the C13 spectrum. And also here you can see the study of the reaction mechanism. So you can study the reaction mechanism with help of the C13 spectra, right? That means the reaction mechanism means, so generally what is the mechanism generally? What is the reaction mechanism? So the steps involved in that particular for the formation of reactant to product formation. So which is follow how many steps it is going to take place, how many steps involving in that in the event of formation of product here, and what are the intermediate compound involved in this reaction, right? And what is the status of the leaving group and the attached group, right? So it is a description. It is a complete study of the all these events. Okay, so here you can predict the reaction mechanism, and you can study the reaction mechanism with help of the C13 spectrum here, right? So for that, generally they are choosing this particular hexamethyl. Okay, the hexamethyl benzene they are taken, and they underwent this hexamethyl benzene is underwent the nitration reaction. And you know that the nitration, it is a electrophilic substitution reaction, aromatic electrophilic substitution reaction, right? So generally, here you see where the normal benzene, okay, the normal benzene chemical shift values is C13 chemical shift values, the carbon, right? This carbon. showing the delta value at 205. Okay, because it is symmetrical benzene here. Okay, so it is a symmetrical one. So you means all the carbons are equal in this one, isn't it? So because all are carrying the methyls, right? So everything is same. So it is a symmetrical molecule. So you have only one. You consider only one carbon, right? So the aromatic carbon. Okay. So aromatic carbon, the delta value is 205. On this particular hexamethyl benzene, the electrophilic substitution reaction, that is the nitration reaction, is takes place here. And then means this reaction proceeds by formation of what intermediate here. Means this reaction is whether it is a uh, SN1 or the SN2 here, right? So whether it is a sorry, not SN1, it is a electrophilic, right? So whether it is a AC1 or the AC2. Okay, electrophilic substitution. SN means nucleophilic substitution. So here the electrophilic substitution follow whether it is proceeds by the concerted mechanism or the non-concerted mechanism. Right? So you know that the concerted, what are the concerted reaction here or the concerted mechanism? So concerted mechanism means the where the single step reaction. Okay, concerted mechanism means the single step where it involves the completion of the reaction in one step. The reactant gives a product, that's all. And non-concerted means where the multiple steps are involved in the reaction. Right? So it proceeds through the formation of the intermediate compound. And the concerted mechanism proceeds through the formation of the transition state. Okay. So you can have the idea, you can get the idea whether the particular reaction is proceeding by means involving the intermediate or whether the reaction is proceeding by formation of the transition state. Right? So this observation will be made by help of the C13 spectrum. So when they are performed this nitration on this hexamethyl benzene, right? So they got this means the substitution of the nitro group on a specific ipso attack. We call it ipso attack because right where the nitro group is attacking on the carbon which is already substituted, right? So this is called the ipso position, ipso carbon. We call the IPSO, ipso here. Okay. So ipso nitration is substitution is takes place here. Then you know that where because here this particular pi bond is conjugate with conjugation with this positive charge. And the positive charge is conjugated with this particular pi bond. So the sequential delocalization of this pi bond is taking place, and you will get the various canonical structures or the resonance structures here, right? And here at a particular point, right? So they got the right, they got the all the carbon, right? All the carbon value at the 18.1 here, right? So this is the very important step in this one where they observe, right? The carbon is showing at a particular point here, not in all the point here, at a particular point. So all the carbons are showing the 18.1, right? Delta value. So generally the 18.1 delta value, it is a alkane range, isn't it? The carbon C13, where the alkanes are here like 0 to 60. Okay, 0 to 60 is alkane, and alkane is above that one here, right? So very least means 0 to 30 or the 0 to 60. That is the range of the alkane means sp3. hybridized carbon, right? But in the benzene, if you see the benzene, there is no sp3 carbon here, isn't it? Because all carbons are right, all the ring carbons here, not the substituents here. The ring carbon, all the ring carbons are right having the sp3, yeah, sp2 hybridization, right? So you see this carbon sp2, this is sp2, this is sp2, this is sp2, this is also sp2 because it is in a planar, right? When the carbocation is in the planar geometry, it will be shows the sp2 hybridization. If it is in the pyramidal geometry, right? Pyramidal geometry, then you get the uh, sp3 hybridization, but it is in the right. So this geometry is the planar geometry. So the planar compound showing the sp2 hybridization. Okay. So here, so you see all the carbons are in the sorry, it's not sp3, sp2. So if you see, if you observe all these carbons are involving in the sp2 hybridization, right? So if it is in the sp2 hybridization, so you are supposed to get the values higher than 60, higher than 100 here, right? But it is showing the 18.1 here. All carbons, right? Groups gives a peak at 18.1. So how come it is? How we are getting 18.1 here? And here it is should be noted that all the carbons showing the 18 same values like benzene 205, 205 here. Okay. So for the symmetrical benzene where it is showing the 205. So like that, here also it is showing 18.1 here. So this is because due to this delocalization, all the carbons are becoming the saturated here, right? Where the unsaturated carbons becoming the saturated due to the where rapid or speedy interconversion or the delocalization or the resonance here, right? So all the carbons, right, means having the equal saturation. That's why where the instrument is showing the this peak or the signal, right? So based on this observation, it is predicted that in this reaction, right? In this reaction, some sigma complex is going to form. The sigma complex is formed here. Okay, by the C13 spectra, by getting this value, it is proposed that the sigma complex is formed during this mechanism. Okay, so this reaction is proceeds by formation of the sigma complex. Sigma complex means sigma bond. All the sigma bond. Sigma means sp3 only, isn't it? Sigma is sp3. Pi is the sp2. So by getting this value, it is proposed that there is a sigma complex involved in the nitration of the benzene, right? So in this way, you can means predict the reaction mechanism also. And yeah, we have the nucleophilic substitution also already discussed here. In general, the benzene won't undergo C. Automatically, it won't undergo C nucleophilic substitution reaction because the benzene itself is acting as a nucleophile because it is excess of electrons, right? It is acting as a nucleophile. So generally, you know that as we discussed earlier, the electrophilic nucleophilic reactions or takes place. No electrophilic reactions and no nucleophilic reactions or takes place here. Right? Means no similar reactants uh, get the reacted each other. Okay. Only where the opposite reagents like electrophile combines or the reacts with the nucleophile or the nucleophile reacts with the electrophile. That combination is takes place in the chemical reaction. But right? When we are providing some special conditions here, in that case, the nucleophilic substitution will be takes place on the benzene, right? So what is that special condition we are providing here, where we are attaching the, right? We are attaching the uh, electron withdrawing groups here, the multiple electron withdrawing nitro groups here, right? So where this electron withdrawing group, nitro group is a, it is a minus Me group here, or minus mesomeric effect group, or electron withdrawing group here, right? So they will withdraw the electron from the benzene ring here, right? They will withdraw the electron. They attract the electron from the benzene. So then the benzene becomes electron deficient and it behaves as a electrophile here. So it will be accept the nucleophile, right? So where the nitro groups making this one as a electrophile here, right? Then the nitro groups making the benzene as a new electrophile. So it is accepting the nucleophile. What is the ethoxide ion, right? So this ethoxide ion can be attack on this particular benzene. Then the nucleophilic substitution will be facilitated, right? In ordinary conditions, in normal conditions, nucleophilic substitution won't take place on the benzene. Okay. So in this way, we can study this one. Next, SN1 nucleophilic substitution. Okay. So this also you can study, means the reaction SN1, SN2 mechanisms also can be studied or the identified uh, with help of the C13 spectra here, right? For example, here some reaction, here some halides. Here. Okay, so you can keep here the halide. Okay, right? So where the by cleavage of the CX bond, by cleavage of the CX bond, where we are getting this carbocation. Okay, the carbocation here, and this carbocation will be exist in the two form. Okay, so here the way the cleavage of CX bond is taking place. So after cleavage of CX bond, so it is leads to formation of a carbocation. Okay, formation of a carbocation, and this carbocation will be, right. The carbocation will be exist in the two forms, or it will be acquire the two geometries or two means what is that? The symmetry, right? Geometry or the structure, for example, right? So one is planar structure or the geometry, and another is the this is pyramidal. Okay, so it will be pyramidal or it will be, right? So here, so it will be exist in the two geometries or the structures here. So this is your planar structure here, right? And the planar structure, okay, the planar structure is or the planar carbonium ion structure. Carbonium ion means carbocation. Carbonium or the carbocation. Okay. So planar structure is exhibiting the sp2 hybridization, right? So as I told you above, the planar structure is exhibiting the sp2 hybridization. So sp2 hybridization generally having the higher delta values. Its delta value means like unsaturation nature, right? So it is showing the higher delta values. And the pyramidal structure, one more structure possible, one more geometry possible after cleavage of the CX bond. Okay, here what means the cleavage of the CX bond takes place which fashion here? It is heterolytic cleavage, heterolysis, not homolysis here, right? The cleavage is taking place unequally, unequal sharing of the electrons. It is heterolysis. Okay. So by heterolysis, you will get the ions, carbocation and the carbon ions. By homolysis, you will get the, if it is homolysis, if it is undergoing homolysis here, you get a radicals. Okay, free radicals here. So this is not taking place and this is taking place here. So we are getting carbocation. So here with the possibility for the acquiring the geometry or the what is that structure is, one is it can be exist in the planar structure which is showing the sp2 hybridization, and it can be exist in the or acquire the pyramidal structure here, right? Here it is pyramidal. It can be in the planar. Okay. So the two possibilities. So if it is in the, if it is acquiring the pyramidal structure, right? If it is acquiring the pyramidal structure here, where this the carbon is showing the delta value 125. This one 125, yeah, delta ppm or j value. Just they are mentioned the j values here. Means coupling constant value. The j value is how much it is 125 heads. Okay, the j value measured in the heads here. J is a coupling constant. The units for this, the coupling constant is heads, and the units for the chemical shift values is ppm, parts per million. Okay, so wherever you observe the heads here, so it is indicating the J coupling constant. So here, so for this pyramidal carbon, the J value is, it is showing the 125 heads, and if it is exist in the uh, planar structure, where the value C13 J value observed is 168 here. Okay, 168. Yeah, this one 168 heads here. And here, for example, if it is okay, if it is exist in the planar structure, you will get the racemic mixture, right? Because the planar structure is means it is having the equal opportunity to the attack the nucleophile on all directions. The nucleophile Y minus can be, it can be attacked from this side or this side or this side or this side. So all the directions, right? It is facilitating for the attack of the nucleophile from all the directions. Then it leads to formation of a racemic mixture here. Okay, and where this, if it is in the pyramidal structure, then in the pyramidal structure, where the nucleophile can be attacked from the front side only. No backside attack is takes place here because there is a means prevention of this group or the hindrance of this R group here. So only the uh, front side attack is takes place. Then you will get the retention of configuration. But here you get the retention as well as the inversion of configuration, right? So the both possibilities you get here. And here, how you are getting the racemic mixture here means when this particular right? So if it is attacking from the front side here, okay, then you get the retention of configuration. If it is coming from backside, then the inversion, we call the Walden inversion, right? The Walden inversion is taking place, then the inversion of configuration is taking place here. Okay. So here the thing is by this C13 spectra, you can able to, right? You can able to predict the geometry of the carbocation which is formed in the nucleophilic substitution reaction. That means whether it is acquiring the pyramidal geometry or the planar geometry, right? If it is if it is exist in the pyramidal geometry, so you will get the value of the 125 heads, J value of 125 heads. If it acquires or if it is exist in the pyramidal geometry, right? The carbocation or the carbonium ion is exist in the uh, planar geometry, then you will get the J value is 168. So based on this, the carbon, right, acquiring which geometry, right? So that will be predicted by the C13 spectrum. Next, stability of carbonium ions. Okay, stability of carbonium ions. So carbonium means carbocation. So you can predict the stability of carbonium ion based on the chemical shift value, C13 chemical shift values here. So generally, the more stable carbonium ion having the higher delta values. Okay, the more stable carbonium ion showing the higher delta values are the downfield. They will show the more downfield and the less stable carbonium ion, right, have the less downfield here or less delta value, right? So here you see this in this particular. Right? So here, acid carbon. Here, acid beta carbon. Where the delta value is 347. Yes, it's like this. Actually, here the more stable, right? The more stable carbonium ion showing the less delta value and less stable carbonium ion showing the higher delta value, right? So because where the right the density, right, the electron density is going to decrease on that particular carbon. So as we discussed in the very beginning first class here, where the electron density is right, electron density is inversely proportional to the chemical shift values here, as in the proton NMR spectra. Also, same formula is applied, same statement is applied here, right? So here you see, so among these, here the tertiary butyl carbocation, and here is a hydroxy group is there, right? And then here some phenol, right? Phenolic carbocation, right? So benzyl, sir, benzyl carbocation is there. Now you see here the benzyl carbocation, and here is a here also methyl is there, and here is a hydroxy is there, and here is only methyl groups are there. In here you can see only the methyl groups here, but in this here you can see the attachment of the phenyl groups, right? So wherever the phenyl group is there, benzene group is there, right? If that carbocation positive charge is conjugation with that particular benzene, then it involves in the resonance. What's the resonance here? So where it means it is acquiring the more stability, right? The resonance is it is a stabilizing factor, right? The region, for example, here benzene. Okay, so here is a benzene where the adjacent this carbocation is there on this carbon with the positive charge is there, right? So you can see carbocation here, and here is a phenol. One more benzene is there here, and some hydroxy group or the methyl group is there on this particular carbocation. Now here you see this carbocation is in the conjugation with pi bond, this pi bond here. So this pi bond will be shifts towards this one. Then this here the carbon positive charge is created. Then this pi bond shifts here. Then here carbocation positive charge is created here. Then this pi bond will be shifts here. So in this way, it is stabilizing by resonance or the by uh, transferring of this pi bond, right? Or the rearranging the pi bonds in the benzene ring. So it is more stable. But here in this methyl, you see, right? So in this methyl, there is no pi bonds here. This methyl is stabilized by in hyperconjugation. Okay, so it will be stabilized by hyperconjugation. But here this carbocation stabilized by resonance. So the compound which is stabilized by the resonance or the mesomeric effect would be the highly stable than the compound which is stabilized by the inductive effect or the hyperconjugation. Right? So the mesomeric effect is more stable than the other stability factors like inductive effect and hyperconjugation. Right? So here this would be the highly stable. Right? So for more stable compound, the delta value is less. For less stable compound, the delta value is more here. So the less stable compounds showing the right means they falls in the downfield and more stable compounds falls in the upfield or the less downfield. Right. The reason is where it is okay involving the resonance or it is getting stabilized by resonance. Next, the dynamic equilibrium. So this is also one of the important application uh, of the C13 spectra here, right? So with the help of the C13 spectra, so you can able to, right, you can able to predict the reaction mechanism here. You can predict the dynamic equilibrium, right? The dynamic equilibrium means the conversion, equal conversion of the uh, reactions, or the equal conversion means equal with the forward reaction and the backward reactions. Okay, the forward reaction and backward reaction takes place with equal rates, with equal proportions here, right? The both reactions you can observe, like forward reaction as well as the backward reactions, right? So the both the reaction is taking place at the room temperature. Okay, so this conversion is taking place at room temperature, right? So voluntarily they will take place here. No apply of the higher energy, no apply of the higher temperatures here, right? So it won't require any the additional, right? Additional like reagents or the additional conditions here, right? So without applying the additional conditions where the interconversion, right, or the forward reaction as well as the backward reaction is taking place. So that will be known whether it is the equilibrium is establishing, right? Whether the equilibrium is established in this reaction or not. That will be studied by help of the C13 spectra. So how can we predict the dynamic equilibrium by C13 spectra? You can see with this example here. Okay. So here, for example, where this right? So this what is it? Ethyl bromide. Okay. Sorry, ethyl bromide. Uh, Carbocation. So ethyl bromide carbocation is for example here initially like here this is one, this is two, right? So just to, you can label the carbons here, then it is easy to recognize this carbons after the reaction is over. Right, so we have labeled this particular carbocation, right? Here is a C1, here is a C2, and it is undergoing the interconversion, right? It is undergoing the interconversion here. So where this bromine is, right? It is shifting on the C1 carbon. Previously, it is on the C2 carbon, for example, right? So after involving in the right equilibrium, it is following the equilibrium where there is a C1, here is sorry, this is C1 here, and this is C2. Okay, so where it is going to attach on the C1 carbon, right? So by this you can say that there is a establishment of the dynamic equilibrium. Means carbonic acid as well as the carbonic acid is taking place. And that will be confirmed by the observation of the chemical shift value, by getting the chemical shift values, C13 chemical shift values in the for this particular compound. Okay. So here this chemical shift of the carbon, right? Chemical shift of the carbocation, it is 310 here. And the chemical shift of the sp3 carbon, here we have two carbons, right? One carbon is the charged carbon, so which is carrying the charge, positive charge here, and another is the neutral carbon without charge. So the neutral carbon is showing the delta value 39, and the carbocation is showing the 310, right? And after sometimes where it is establishing the dynamic equilibrium, and it is going to, right, the changing of the position of the bromine is taking place, right? And it is showing the value, means some different, okay, in addition to this particular 310 and 39. Okay, so in general, we are supposed to get these two values here. In general, we are supposed to get these two values, for example. But in this particular, when we are recording this C13 spectrum of this one, so in addition to this C 310 and 39 peaks, so we'll observe one more peak also at 75.6, right? So this 75.6 peak is observed. So how we are getting means generally because there is only two carbons, isn't it? So in the C13 spectra, the number of signals is equal to the number of carbons, isn't it? In the C13 spectra, the number of non-equivalent uh, carbons equal to the number of signals. So in this particular compound here, we have only two carbons, isn't it? One is charged carbon, positive charged carbon here, carbocation, and another is a neutral carbon. So only one and two, only two carbons are there. So two different carbons are the two non-equivalent carbons here. So we are supposed to get only two signals, isn't it? Because number of different carbons equal to number of signals. So as per this, we're supposed to get only two signals here. But in addition to these two signals, we are getting one more signal also, right? We are getting one more signal. So how we are getting this? Why we are getting this? Because, right? So despite of the two carbons, we are getting the one more signal, right? If you get the three signals means there must be a three carbons here, but there is no three carbons, isn't it? There is only two carbons. So how we are getting this? Wow, and what this signal? What for this signal here, right? So it is means by keen observation of this one is by getting this that additional signal in the C13 spectra, right? It is gave the evidence for the right interconversion of the that carbocation at equilibrium state. Okay, so at equilibrium, it is interconverted from forward to backward, backward to forward. So by this interconversion, the instrument is observed a different carbon here. Right? So when in the forward reaction, for example, okay, so in the forward reaction where this particular uh, right, so C13, right, the carbon, one carbon is showing 310 and another is showing 39, for example. So after the interconversion, the whatever the carbon carrying the positive charge, it is showing 174 here. Okay, 174 signal. So then it is known that, right, 175 by 2. Right? Okay, the average value. We are taking the average value. So we are getting a different signal at 75. Right? So this is getting due to the equilibrium, dynamic equilibrium here. Okay? So at dynamic equilibrium, that carbon is behaving because where the attachment of means this detachment of bromine is taking place and attachment of here is taking place, right? So in between, right? So where the period for this transferring bromine from here to here, it is a transition period. The transition period is it is giving the signal at 174, not at 310, not at 39 here. It is showing the 174 here at transition time. Okay, so it is known that that particular interconversion is taking place. And one more observation is where this shifting of this particular bromine from one carbon to another carbon through the formation of the through the formation of the cyclic bromonium ion. Okay, so this particular means bromine transferring from this carbon to this carbon here, right? Through formation of the cyclic bromonium ion. So in the cyclic bromonium ion, we know that okay. So if the cyclic bromonium ion is formed, right? So here this is the compound where we, we are taken this, right? This is a carbocation. Okay. So so for this we are getting how much it is? Values C13 values 39. Okay, 13 EP. And for this carbon, okay, charged carbon, how much we are getting? 310. Okay, 310. Right? But in the C13 spectra, we are getting one more signal also. For example, this signal is for 39 here, this carbon, and this signal is for 310, for example. But in between, one more carbon, one more signal is there at 175 here. Okay, so how we are getting this 175? Because there is only two carbons, but it is showing three signals, right? So that is because in bit means it is undergoing this dynamic equilibrium, and the dynamic equilibrium is established through this formation of cyclic bromonium ion. Okay, so where this bromine, because the bromine is having the non-pair electron, non-bonded electron, so it is going to attack on this one. Then what is happening here? Some bromine ion is cyclic bromonium ion intermediate is formed. Now here it is symmetrical. Cyclic bromonium ion is symmetrical here. So these two carbons are equal, isn't it? If it is in the acyclic form, these two carbons are different. But if it is in the cyclic form, then these two carbons becomes equal here. So the instrument is giving the value at 174.5 or the 175 approximately for this carbon, right? So this value is getting due to formation of the cyclic bromonium ion. So we are getting three signals here. Okay. And again, this is right. So again, after formation of this one, then by cleavage of this bond, right? So again, it is going to means this is forward reaction. Then the backward reaction is taking place again. The backward reaction is taking place. So where this bond cleavage is taking place, and again the retention of right, that is reinstitute of that particular material, starting material, right? So due to this one, we are getting three signals. So by this, we can establish the mechanism also. Okay. And one more example here is same. Here, actually, here is carbon, not right, this is not oxygen here. This is carbon only. Right? So make it correction here. This is carbon only. So where this okay. So here generally for this compound. Okay. So for this compound. So how many non-equivalent protons are there? So non-equivalent carbons are there generally. Here these two are same, right? Okay, so these two methyls are same, and these two methyls are same here. Okay, so you get one signal, one, and for this you get two signal, and for this you get the three, and for this you get a four. Okay, so it gives up four signals here, right? You get the four signals for this. Means when it is uh, positive charge is there, then you get a four signals. If there is no positive charge, you get only two signals only, right? There is no positive charge, then you get two signals because it is symmetrical one. You get here, you get this is different and these two are different here. Here also same, but if there is a positive charge, you get a four signals here, right? And so in general, okay, so it is giving the four signals, but practically means like, when you are recorded the C13 spectrum, theoretically it is calculated there is a four signals, isn't it? Here, this is these two are one, same chemical environment here, you get one signal, and for this carbon you get two signal, and for this carbocation positive charge carrying carbon, it is different, so you get third three signals, and this that is two methyls on the carbocation. They gives appears as different, so there are four signals here, isn't it? So in general, as per the theoretical, right, theoretical validation, you are getting the four signals here. But the C13, when we are recorded the C13 spectra, so it is showing only two signals here, right? As per the theoretical observation, you are right. So we'll get the four signals here. But experimentally, it is giving two signals, right? And one signal is appears at 63, and another is appears at 346. Okay. calories appears at 346. So then how it is takes place? Okay, how it is taking place here. Then here, okay, so we are getting means as per this, we are getting two okay two values are the two signals means there must be two carbons here, but here different carbons, but here we are observing four different carbons here, right? So for getting this instead of the four signals, by getting the two signals, it is indicated that this compound is undergoing the dynamic equilibrium. That means this charge, positive charge is shifting from this carbon to this carbon, right? Or from here to here. So it is a the continuous process where the shifting of this one is taking place here. At equilibrium, right? So it is going to means this positive charge. Sometimes it is exist on this carbon, and sometimes it is exist on this carbon, right? So it is a the shifting of this positive charge from this carbon to this carbon. It is taking place. Due to this shifting of the positive charge from this carbon to this carbon, so the instrument is giving only two signals here because right. So because you know that it is a rapid interconversion. So generally for the speedy interconversion, the instrument cannot be recognized that way, right? So where the instrument is identifies only this carbon and this carbon here, right? Because where this positive charge, if this positive charge is on this carbon, then again you get same, is it? So if it is present on here, then you get same here and here, right? So where this proton is shifting here. So in this way, due to this dynamic equilibrium, establishment of the dynamic equilibrium, so it is giving the only two signals. One signal at 63 here, and another is at 346 here, right? That's why we are getting the two signals instead of the four signals here. And that will be confirmed by the values like the if you do the average values of here, you get this one. Next, the degenerate rearrangements. So by this C13 spectra, you can predict the or you can study the rearrangement. Right? You can observe the degenerate rearrangement mechanism. Okay. So what is degenerate rearrangement here? Degenerate rearrangement means where where the starting material, the reactant, right? After the reactant undergoes a rearrangement reaction, and the product, the formed product must be have the same structure. Okay. So here the reaction takes place. Okay. But where after the reaction, where the obtained product also having the same structure here. So that is called the degenerate rearrangement reaction, where the structure of the reactant is same as the structure of the product, or the structure of the product is same as the structure of the reactant. That is a degenerate reaction. Okay, so this whether by this C13 spectra, you can predict whether the degenerate rearrangement is taking place or not, or if it is taking place, by what mechanism it is, means what pathway it is taking place here. Right? So you can predict the reaction pathway with help of the C13 spectra. Okay. So for this particular, what is this some keto ester? Okay, alpha, yeah, alpha keto ester is right. The cyclic alpha keto ester is undergoing the degenerate rearrangement reaction in the presence of the potassium acetate here, right? Potassium acetate, and you see here this and this one. This is the reactant. This is the product. This is your product here. This is your reactant, right? So you see, the, both the compounds are having the same structure, right? So these two are same here. Both are same, isn't it? Both are same. But if you but the only thing is where the position of the carbonyl is going to change. Okay, the position of the carbonyl is going to change. For example, just you label for better understanding, you can label this carbonyl. For example, is three, for example, right? Now see, there is one, there is a two. So what is happening here? Earlier, the reactant where the carbonyl is on the C1 carbon, is it right? The C1 carbon is a exists as a carbonyl. So after the rearrangement reaction, or after the reaction here, right? After the thermal reaction, some chemical changes is taking place, and on C1 carbon, the ester is takes means the ester is attached here. Earlier, on C1 carbon, the carbonyl group is there, CO group is there. But after the rearrangement on C1 carbon, the ester there is a ketone, right? Yes, it is ketone. C1 carbon is ketone. And after the rearrangement reaction, not after the reaction, the C1 becomes a ester and C2 becomes ketone. In the reactant, C1 is a ketone, C2 is a ester. In the product, C1 is a ester, C2 is a ketone here. That means what is happening? The position of the functional group is changed. Okay, the exchange of the interconversion of the functional groups here, or the exchange of the position of the functional groups is taking place here. Okay, so for acquiring this, for the conversion of this right product, but the structure is same. You see, okay, the way the structure is same here. Only the position is changed, but the structure is same here, isn't it? So for this conversion, right? So what pathway is means this conversion taking place by which pathway or how this conversion is taking place that can be established by C13 spectrum. Okay, so we'll see. So for this conversion, we'll propose two mechanisms here. Two mechanisms, or the pathways we see. Mechanism or the pathway. Right here in the pathway one, just to take the pathway one here. Right? So in the pathway one, right? So what is happening where is CH bond shifting towards this carbonyl. Then this pi bond is attacking on this carbonyl of the ester. Then CO bond cleavage is taking place. Okay, so some internal rearrangement reaction, right? The internal rearrangement reaction is taking place. Then we are getting some right? Some what is this? Some oxidane, yeah. So here is I think oxidane intermediate is going to form, right? Some oxidane intermediate, oxidane. Okay, so some oxidane intermediate is taking place here. Now then, by shifting of the CO bond here, the cleavage of CO bond, this bond cleavage by right the repolarization of this one, right? So this is polarizing on this oxygen. This pi bond is polarizing on this oxygen due to the attachment of this CO bond here, attacking of this CO bond. Then some cyclic, right? Some oxygen cyclic intermediate is formed here. Now the repolarization of CO bond towards this carbon, then the cleavage of this cyclic intermediate is taking place. Then this pi bond is shifting here, then we are getting this one. Okay, and you see here, right? So what you are observing, right? So here you see, is this pi bond. Okay, so this pi bond is just it is exists as a minus here, and where this proton is leaving here, this proton is attacks with this negative charge, and it is gets neutralized. Okay. Now you see earlier in this particular keto ester, earlier the C1 carbon, right? So this C1 carbon is carbonide here, keto. Now here you see the C2 carbon is becoming keto, right? So here by shifting of this, right, the bond towards this one, so it is becoming C double bond here, and this is going to form the C single bond only. Okay, and where the ester is shifting on the C1 carbon. Okay. So now you see in this particular internal mechanism reaction here, where it is going to form as a, right, so it is going to form as a ketone here, and it is going to form as a this, and the entire part is, right, formed as a ester. Okay, so here is a C1, this is C2. Okay, so where the C2 becomes in carbon. Now we'll see another pathway. This is the pathway one. We proposed the pathways here. Next pathway two here. We'll see. So the pathway two, what is happening here? Right. So here is a proton. Right? So this proton is shifting towards this carbonite. Okay. Then it is means some enolization, right? Tautomerism. By tautomer keto enol, tautomerism. Okay. So by tautomerization, we are getting this intermediate compound. Right. Now this particular, right? So where this pi bond is, okay, so this pi bond is in here, then this is, look, so this OH, right? So this is shifting towards this one, then here this will end this cleavage of is shifting towards this one, then this cleavage of this one is taking place. So, and we are getting this product. So what do you observe here? Right. So here this particular OH group, right? So this CO carbonide. So carbonyl initially it is undergoing the enolization, okay, ketoenol tautomerism, and then okay, so the way the position here only the OH CO becoming OH, and the OH is again repolarizing here, and we are getting this one. So what is happening here? There is no change of the OH carbonyl position here, right? Carbonyl position is not changing, right? So where the where means the carbonyl compound carbonyl group is present on the C1 carbon. In the initially it is on the C1 carbon. After also it is in the C1 carbon. right? There is no change in the carbonyl position here. Okay. So where the position is retained for the carbonyl for the ester, the rearrangement is taking place here. Okay. So the rearrangement is taking place, but after the rearrangement, okay, after the rearrangement, both the functional groups taking their original positions here. They are not exchanging the positions. They are not exchanging the carbon's positions here. Both are coming back on their original positions, right? But the changes means the rearrangement is taking place, but after the reaction where they are getting same positions here. So there is no change in this one position of the carbon. But in the pathway one, what is happening? Where the changing of the position is taking place, right? Because this C1, right? C1 is becoming the ester, C2 is becoming the carbonate. Okay, so the pathway one is correct for this degenerate rearrangement reaction, and that will be confirmed by the carbon-carbon coupling reaction, right? Okay, carbon-carbon coupling reaction. Because in the C pathway one, there is a carbon-carbon coupling because the position is of this carbonyl group and ester group is changing, right? So where the coupling of this carbon-carbon is taking place. But in the pathway two, there is no exchange of the groups, right? So on what carbon they are attached, so that position is retained after the reaction. So there is no coupling. C3 coupling is observed for this pathway two. That's why the pathway one is correct for this one, right? Where the carbon-carbon C13 coupling is observed in the pathway one. So the pathway one is correct for this degenerate mechanism. So by this, you can predict the correct pathway for taking off this rearrangement here. Next, carbanions. Carbanions means negative charged species. Now we can establish or we can predict the carbanion strength or the capability or the capacity. So we will have this particular the Grignard reagents here and Gilman's reagents. Alkyl methyl, right? So alkyl lithium, alkyl magnesium bromide, right? So here, among these two organometallic reagents here, right? These are the organometallic reagents. So which organometallic reagent is more efficient, right? Or more reactive? The more reactivity character can be decided by the C13 spectrum. Okay, so which is showing the less chemical shift value is a more reactive, right? So the whose carbon, right, having the less chemical shift value is a more reactive organometallic reagent. Now you see in this methyl magnesium, right, methyl magnesium bromide, it is showing the delta value of minus 13.6, and methyl lithium, it is having a minus 16.6. And here this particular ethyl magnesium bromide, right? Ethyl magnesium bromide, its value is minus 2.9. Okay, so whose minus delta values is more, that will be the more reactive, less stable or the more reactive. Okay, so you see this methyl lithium is a more reactive because its value is very less. Okay, and its value is more somewhat more, and it is minus 2.9 means higher, right? Higher temperature values for this ethyl magnesium bromide, and this is reactivity order. Methyl lithium is a more reactive, then methyl magnesium bromide, then ethyl magnesium bromide. right? So by this you can predict the reactivity of the organometallics also. Okay, so this is the application of your C13 spectra, and here is some exercises are given. So here you see this particular examples, right? So it is some the values are given, right? So here is the molecular formula is given here, right? So the molecular formula C5H11 Cl, and the C1 carbon 13.9 quadrate here, C2